Hi, welcome to the presentation of our final project in CS 4701 taught by Professor Bart Selman at Cornell University. Our project is called Tasking Evolution to Rear Intelligent Systems, and it is a genetic programming approach to playing Tetris. It's by Victoria Benson and Ali Meng. Of course, most of us are familiar with the grid-based video game Tetris. As soon as the game starts, there are blocks called tetraminos that drop from the top of the screen, and the objective is to put them in such an orientation such that when they drop, they create the most complete horizontal lines of bricks. When a horizontal line is created, it is cleared, giving you points. And after this line is cleared, the blocks that are on top of the line now drop down a space to fill in the gap. The game is over when blocks stack up so high that they touch the top of the screen. Our goal in this project was to develop a bot to effectively play Tetris. To do that, we used an organic algorithm that mimics natural selection. As a basic overview, the bot looks at every place on the grid that a tetramino could fall onto, as well as every orientation that block can take. Then, the bot uses an equation to compute the quality of each of these possible positions. This equation is developed by our genetic programming algorithm. We evaluated and ranked these bots based on how many lines they could clear within the first 100 tetraminos dropped, or until they lost the game. Okay, now let's dive deeper into our algorithm. Genetic programming is a more advanced version of the well-known genetic algorithm. The difference is that the genetic algorithm simply uses an array of bits to represent individuals in a population. Our project, however, uses trees. These trees are called parse trees and allow for a closer representation to biological genomes because trees have an infinite set of genetic possibilities for each individual. Arrays from genetic algorithms, on the other hand, only have a set size. So in the genetic programming algorithm, we start off with a parent population of trees that are randomly generated. Then the performance score, or fitness function in genetic algorithm terminology, for each of these trees are determined. The top performing trees are then selected to reproduce and create new trees, simulating natural selection. Reproduction is done by a crossover, which is combining two parent trees in some way to create children trees. And then, to simulate genetic mutation, a small part of each child tree is modified. In our project, we also kept the best performing parent tree without change to preserve it. Now let's talk about what parse trees look like. Parse trees consist of two types of nodes. The first one is an operator node, which contains a function from a function set. In this project, we chose our function set to contain addition, subtraction, multiplication, and division. These operator nodes have two children nodes, which can either be another operator node or the other type of node, a leaf node. Each leaf node denotes a value. These values are described in the next slide. Here, you can see an example of what a parse tree looks like. This tree computes the value 22. You can find this value by doing 5 times 3, which is 15, and then 15 plus 7, giving you 22. So our bot calculates the values that are put into the leaf nodes. We have 4 core values. These are lowest y, highest y, num adjacent filled, and num underfilled. These values directly measure the performance of a tetramino. The fifth value is tetramino ID, and finally, we have an integer between 1 and 10 that can be used to weigh or adjust certain parts of the tree. Okay, so now let's look more closely at how trees are crossed over. The top performing trees in the previous generation are used as parent trees. We randomly select a node from each of 2 parent trees, and then we swap these 2 nodes along with all of their children across the 2 trees. Let's take a look at what this looks like. Here, the addition operator node on the red tree has been randomly selected to cross over with the 7 leaf node on the green tree. So after these children trees are created, we mutate them by randomly choosing between 2 methods. The first method is called modify an existing node, and the second method is called add to tree. Let's see some animations to clarify how this is done. In modify existing node, this division operator has been randomly chosen to be modified, and a multiplication operation has been randomly chosen to take its place. Now, in add to tree, this 9 leaf node has been randomly selected for mutation. we create a new addition node as a new operator node and a new leaf node with a value of 7. We then place the 9 node as one of the children in the new set of nodes. And finally, we put the addition node in the place that the 9 node was originally found. Now I'm going to run through specifically how we train our bot to find an optimal tree. First, we started with a randomly generated tree population of 13. We then ran a game of Tetris, using each tree to determine the top 4 performing trees, with the fitness function being the number of lines cleared in the game. New trees were created by crossing over each of the top performing trees with each of the other top performing trees, and using an order matters approach, giving us 12 new children. We mutated the newly created children trees, and this created the new tree population, along with the best performing tree from the previous population. We repeated steps 2 through 4 for 30 generations. After running our program many times and tweaking the input parameters in each run, here you can see our best performing tree. It is surprisingly simplistic and seems to imply that highest y, num adjacent filled, and num underfilled are the most important factors in determining how to orient and place a falling tetramino. Using this tree, our bot was capable of clearing 19 lines per 100 tetraminos. It's important to note that because we only dropped 100 tetraminos, 100 times 4 for each block of a tetramino is 400. Then 400 divided by 20, which is the width of the grid, is 20, meaning that the upper bound for the number of lines that could possibly be cleared in a perfect performance is 20. However, this requires that the tetraminos that fall are in a certain order so that perfect lines can be created using all of the 100 drop tetraminos. As tetramino selection is random, this perfect scenario is very unlikely to happen. A more realistic upper bound is probably actually 19 lines. This indicates that our bot displays perfect performance under the given tetramino conditions. Here you can see some statistics in the creation of this tree. You can see that this tree, or a tree that performed just as well as this tree, was found after only 7 generations, as indicated by the max number of lines cleared column. There were many other trees that were developed by changing various factors. These factors included the number of generations, the population size, and leaf input values. Okay, now we're going to demo for you 2 of the other trees that we developed, and of course, our best performing tree. Here's one of the earlier models we ran. We used 4 top performing trees, a population size of 12, and the values in the leaf nodes are lowest y, highest y, num adjacent filled, tetramino ID, and an integer between 1 and 10. As you can see, this model did not perform very well as it lost while only creating 3 lines. This game shows a use of our top performing tree. It was created with the input parameters of 4 top performing trees, a population size of 12, and an added value called num underfilled. We also cut down on the additional values to 2, 5, and 10 rather than the 1 through 10. This game will likely run forever, as with this run we did not limit the number of tetraminos that could come in. This third demo was created by using a tree that was developed later on. It doesn't perform as well as the second one, but it is comparable. It has a distinctive feature in which it tends to build up walls of blocks and then fill in those gaps. The only input parameter we changed in this run compared to the previous run is that for every generation, we added in the previous top performing tree with no mutations, no changes. Alright, so that wraps up our presentation. Thank you for watching.